And hello, Science 20. Hey, we are back. We're going to keep going in our exploration of physics. So just give me a minute to bring up the slideshow. Last lesson that we had, we were talking about uniform motion. And so uniform motion, as you recall, is where the speed or the velocity is constant. And if we were to draw that on a position time graph, we would just see a straight line. Now, it could be a straight line horizontally, which means there's no motion, which is still uniform motion, or it could be a sloped line, which could show either positive or negative velocity. Uh, but then the question becomes, well, what do we do when it comes to non-uniform motion? What does that look like? And as you can see here, in non-uniform motion, we see a curving of these position time graphs. Let me just fill in that little bit of empty space there. But yeah, we would see this curved line representing that the velocity is not constant. And so to determine the velocity at any given point is going to be very tricky to do that when the graph is a curved line. But anyways, this brings us to our topic of today, which is acceleration. And acceleration, it's a vector quantity. It is non-uniform motion. Most of the time when we think about acceleration, we think about speeding up. So that means, you're in your car, you're at a red light. Hopefully you've stopped, haven't gone through the red light, but you've stopped in your red light and you're waiting for it to go green. And at that moment, uh, the velocity of your vehicle is going to be zero. I'm just going to move this over a little bit so I can, there we go. But when it comes to when the light goes green and you start to accelerate, that's going to give you acceleration. You're going to be changing your velocity, and it's going to be continually changing until you reach your final velocity. Likewise, if you're driving along the street and you see a light turn yellow, you hit the brakes and that starts slowing you down. That's what we call negative acceleration. Your velocity is getting slower until you come to a complete stop. So we're going to look at acceleration in terms of a velocity time graph. Now, the x-axis is going to represent the y, or sorry, the velocity will be on the y-axis. X-axis will be time, and at this point here, when we get to the bottom of the y-axis, that means that we have reached zero velocity, or we have come to a stop. Now, the slope of a velocity time graph is going to represent acceleration. Now, again, because acceleration is a vector quantity, we need to include the direction all the way throughout our work. Now, it is also important to note that the steeper the slope, the more speed is increasing, or the more quickly speed is increasing. So in this graph up here, we notice that this line here, the slope is very steep compared to the black line, which means the red line, this object is accelerating at a faster rate than the black line is. Now, to find the slope, it's just rise over run. So change in velocity divided by change in time. And I want to point something out here. When we have our change in velocity, which is meters per second, and we divide that by seconds, that is the same thing as, and remember that, just let me show you over here. So meters per second divided by seconds is the same thing as meters per second times the reciprocal, which is 1/seconds. Therefore, the units for acceleration are going to be in meters per second squared. Okay. Now, when we look at a velocity time graph, and so we would use the slope to represent acceleration. So here on this line, this horizontal line here, we have no acceleration because the change in velocity is zero. We're not changing the velocity. Here we are experiencing acceleration. But an interesting little tidbit about acceleration, or sorry, about a velocity time graph, is that if you look at the area under the line, you can actually calculate your displacement. And let me show you the units on that. So let's take a look at this rectangle here. So in this rectangle, the area of a rectangle is length times width, right? So area of a rectangle is length times width. The length is going to be your time in seconds, and we're going to multiply it by the height, which is in, sorry, that should be a height times width. Doesn't matter. Height times width, and that's going to be seconds times meters per second. Well, that means the seconds are going to cancel each other out. So your units that you're going to be left with are meters. So that's how we know that this is the displacement, because the units will give us a change, or the units will work out to be in meters. Now, in a sloped velocity time graph, you're going to get a triangle. And when you get the triangle, it's just base times height over 2. So times multiplied by velocity divided by 2. Again, the seconds in the units cancel out. You're left with a level, or a measurement in meters. Okay, let's run through a couple examples of this, and then you'll have some practice to work on. But starting off here, so we're being asked to calculate the acceleration of this graph. Well, the acceleration, the final velocity is 3 meters per second north. The initial velocity is 3 meters per second north. We're looking at a 5-second interval. So 3 meters per second minus 3 meters per second is 0. 5 minus 0 is 5, but 0 over 5 is going to be 0. So we have no acceleration for this horizontal line. The displacement is just length times width, 5.5 seconds times 3.0 meters per second. And we end up with 16.5 meters. Again, though, we're going to keep an eye on our sig digs. Sig digs are going to equal 2 for each of these. So that's why our final answer is going to be 17. How would we describe the motion using everyday language? Well, the velocity is going to stay the same. The object is moving, but the velocity is not changing. And we would describe this as uniform motion and no acceleration. All right. Okay. So now we're going to switch to this one here. We've got ourselves a sloped line for a velocity time graph. So we're going to find the change in velocity. So we're starting, and you can pick this anywhere, because this is a straight line. We could really go anywhere we want to and find out. So I'm going to draw my line here. So we see that the change in the velocity at this point, we start at 0.5 meters per second. We end up at 4 meters per second. So 4 minus 0.5 is 3.5 meters per second. The time is from 0 to 4 seconds, so that's going to be 4 seconds. 3.5 divided by 4 is 0.875 meters per second squared. Again, 2 sig digs, that's going to give us 0.88 meters per second squared. Now, the displacement is going to be a little trickier here, because you'll notice we're not starting at 0. So I'm just going to draw a bit of a dotted line here to kind of divide the graph up into 2 places. Now, our first area is going to be this part here. So it's a really long, skinny rectangle. So It's 5.5 seconds in length. It's 0.5 meters per second in height. So we're going to multiply those two together to come up with the area for that section. But then we have the triangle section here. And so in our triangle section, we're going to use the base times height divided by 2. So the base is going to be 5.5 seconds. The height, we're going from 0.5 up to about, now you're going to have to estimate here, but I would say that probably be a 5.4 meters per second. And so we're looking for, we're then going to be looking for 5.4 minus 0.5, which is 4.9. So that gives us the area here. So we've got 5.5 seconds times 0.5 meters per second. I'm just going to grab my calculator. I don't have it here, but I'm going to grab my calculator and just quickly calculate that for us. 0.5. And so this part is going to equal 2.75 meters. And we're going to add to that this other part. And so the other part is 5.5 times 4.9 divided by 2. And that's going to give us 13.475 meters. We're going to add those two together. So I'm going to add 2.75 to the 13.475. And we end up with 16.225 meters. Now, this is a displacement because we're dealing with velocity. So we're going to put our positive sign in there to show that this is moving in a positive distance, in this case, moving north. Sig digs, we got 2 sig digs in our multiplications. So that means if we were to round our areas, we'd round them to 2 sig digs. So then that would give us 2 sig digs in our final answer. 16.225 would become 16 meters. What would we say about this? Well, the object is getting faster. And in physics terms, we would just say that this is non-uniform motion, positive acceleration. One more example we'll do together, and then I'll let you guys do some work on your own. But when it comes to this graph here, where we see we're going down, we're starting at a high velocity, and we're going to be dropping down to a complete stop. And so in this case, to calculate our acceleration, the slope of this would be the chain. And again, you can pick your spot anywhere you want to. And it looks like in this particular example, they're putting this as our token spot. And so we're going to be looking at the change in time as being 3.5 seconds. So that's the 3.5 times or minus 0. And the change in velocity is going to be, we're starting at 6 meters per second and we're ending at 2 meters per second. So it's always final minus initial, or y2 minus y1. And so that's going to be 2 meters per second minus 6 meters per second, giving us a negative 4 meters per second. So we divide that by 3.5. And just give me 1 second here. 1 point. Okay. So we're going to get a repeating number. But what it works out to is negative 1.14. Let me just give you a few more decimal places. 286. Okay. So again, we want to round for a correct number of sig digs. 2 sig digs here, 2 sig digs there. So negative 1.1 meters per second squared will be our total acceleration. Displacement, since we're starting at time equals 0 and we're ending at time equals about 5.3 seconds, and we're starting at a velocity of 6 meters per second and an ending velocity of 0, that means our displacement is going to be simply base times height over 2. We just have a triangle in here in this area. Okay, nothing else. So we're going to find the area under the line here. Time, 5.3 seconds. That's the length of our base. Height is 6.0 meters per second. Now you might be saying, well, wouldn't that have to be a negative because we're slowing down? No. So what we need to remember is that even though we are decreasing in our velocity, we are still moving in a positive direction. So the displacement will stay positive. So that's going to be 5.3 times 6 meters, 5.3 seconds times 6 meters. And we end up, and then we divide that by 2. We end up with 15.9 meters. And again, for 2 sig digs, that means as we're coming to us, if you're traveling at 6 meters a second and you hit this level of acceleration of negative 1.1 meters per second squared, you're going to come to a complete stop after traveling 16 meters in the forward direction. Now, how would we describe this in everyday language? Velocity is decreasing, so object is slowing down. We would say in physics terms that we have a negative acceleration and that the that the motion here is non-uniform motion. Okay. All right, so practice problems, work on these at home. I might go through a couple of them with you in class, but you definitely need to be doing your work here with this. And so I want you to describe the motion. So you just have to use words for this one. Determine the acceleration. So that's calculating the slope of the graph and then determining the distance traveled by the bicycle. So that means we're going to try to find all the area underneath the line. So in this specific problem for practice, problem number 1, we're going to be looking at the area of this triangle and the area of the rectangle below it. Similar thing in number 2, asking to calculate the exact same things. Number 3 is going to be interesting because number 3, you are traveling at a certain speed, then you're slowing down but not coming to a stop, and then continuing at that new speed. And once you're done that, there's some homework for you to be working on. But that's all that I have for you guys today. So if you have any questions on anything, feel free to ask. Please do those practice questions, and I'll look forward to seeing you in our next video.